behalf of the School of Arts and Sciences and Penn Engineering, I am very pleased to welcome you to today's Philosophy Colloquium, at which we are hosting the 9th annual Thomas and Yvonne Williams Lecture for the Advancement of Logic and Philosophy. We are most grateful for the generosity and vision that Tom and Yvonne have shown in establishing the fund that supports this series of lectures and that makes possible other educational activities at the university and at upper schools in our region. It was a great pleasure to work with Tom when I first arrived at Penn and to watch him develop, through the study of logic and philosophy, that clarity of mind which he has so successfully brought to bear in the sphere of practical affairs, and that sustains his ongoing passion for the life of the mind. And it remains a great pleasure to work with him now on a range of activities that will advance a general appreciation of the power of reason to clarify problems, both practical and theoretical. I am delighted to introduce this year's Williams lecturer, Hilary Putnam, and to extend to him the very warmest Penn welcome on behalf of President Gödel, who regrets that she cannot join us today for a stimulating talk by one of our most eminent alumni. Dr. Putnam received his BA from Penn in 1948, majoring in philosophy and, as I learned today, in German and linguistic analysis. In 1985, the university paid tribute to Dr. Putnam's extraordinary contributions to logic and philosophy with the award of an honorary Doctor of Humane Letters. In mathematical logic, his fundamental contributions include results leading to the resolution of Hilbert's 10th problem in collaboration with Martin Davis and Julia Robinson, algorithms for the Boolean satisfaction problem in collaboration with Martin Davis, and pioneering investigations of the fine structure of Gödel's hierarchy of constructible sets. In philosophy, he is among the most influential thinkers of our time. In 2010, he received the Prometheus Prize of the American Philosophical Association in recognition of his lifelong contribution to expanding the frontiers of research in philosophy and science. In 2011, he was awarded the Ralph Schock Prize in Philosophy and Logic for his contribution to the understanding of semantics for theoretical and natural kind terms, and of the implications of this semantics for philosophy of language, theory of knowledge, philosophy of science, and metaphysics. And in 2012, he was honored with the Launer Prize in Analytic Philosophy. Dr. Putnam is Kogan University Professor Emeritus in the Philosophy Department at Harvard University. He is a past president of the Association for Symbolic Logic, the American Philosophical Association, and the Philosophy of Science Association. He is a fellow of the American Academy of Arts and Sciences and the American Philosophical Society, and a corresponding fellow of the British Academy and the French Académie des Sciences Politiques et Morales. Please join me in welcoming Hilary Putnam, who will speak to us about how logic morphed from museum piece to marble.
All art lovers know, as all art lovers know, museum pieces can have great beauty, and in their own times, they are often the beginning of new ways of seeing, thinking, and creating. That's also the case with ancient logic. Aristotle had the insight that gave rise to the whole subject of logic, the insight that valid inferences in which the conclusion, as we say, follows logically from the premises, depend for their validity simply on their form. For example, not only is this a valid syllogism, all human beings are mortal, all Greeks are human beings, therefore all Greeks are mortal, but so is every other inference of the logical form, all S are M, all M are P, therefore all S are P. Aristotle did use letters, alpha, beta, gamma, not Latin letters. In present-day terminology, S, M, and P, or his alpha, beta, gamma, are predicate variables. Aristotle invented the variable. By the way, letters for variables in algebra in Europe date from the time of Descartes. Aristotle studied in detail the properties of 256 inferences called categorical syllogisms, or simply syllogisms, in which each of the premises and the conclusion has one of the four forms: all S are P, some S are P, some S are not P, and no S are P. Actually, the form written SOP and some S are not P, Stephen Reed points out in a very important article published, I think, just last year or the year before, that Aristotle's Greek actually prefers the reading not all S are P. And if you read not all S are P, SOP, as not having existential import, and all S are P as having existential import, that is, all S are P implies that there are S's, but SOP does not imply that there are S's, then the square of opposition is correct. There's no problem with, there's no confusion about existential import in Aristotle. Rather, a late day to discover that, but a delightful discovery. Anyway, then Aristotle showed how to determine which ones are valid. The 24 are valid, of the 256 possible syllogisms are valid, and the great majority are not valid. By doing this, he launched the program of creating an organon of deductive reasoning, a systematic account of the modes of valid deduction. In one stroke, he gave us the notions of logical form, logical validity, and the program I just referred to. How this magnificent achievement became a museum piece is a long story, and this lecture is about modern logic, so I shall be brief. The most important of Aristotle's successors were the 3rd century before the Common Era Stoic logicians. And among their achievements were the beginnings of what we today call propositional calculus. In the so-called Dark Ages, which really were dark as far as logic is concerned, not only was Stoic logic forgotten, almost all of Aristotle's books were lost to the Latin West. The logical work De Interpretatione was one of the two that was known in the Dark Ages, even in the Dark Ages. Many more works by Aristotle became available in the 12th century, and there was a sort of revival of logic in the 13th, which recent scholars have done a lot of work on, but almost all Stoic texts had been lost. And Stoic logic never became part of the curriculum in the High Middle Ages. In fact, it was 20th century scholars who rediscovered Stoic logic. That is perhaps partly explains how Kant could write in the preface to the 2nd edition of the Critique of Pure Reason, quotes, "Since Aristotle, this logic," referring to traditional logic, "this logic has not been able to advance a single step, and is thus to all appearances a closed and completed body of doctrine." To all appearances, a closed and completed body of doctrine. At this point, logic really was a museum piece. However, in 1847, George Boole, a British mathematician who made important contributions to many fields, including the theory of differential equations, the calculus of finite differences, and probability theory, published the first of 2 revolutionary works on mathematical logic, the mathematical analysis of logic, followed by his masterpiece in 1854, The Laws of Thought, or to give its full title, An Investigation of the Laws of Thought on which are founded the mathematical theories of logic and of probabilities. And Boole made it clear that Aristotle's logic was only a fragment of what we know as deductive reasoning, a view in which he was a little later joined by Augustus de Morgan. Boole knew, of course, of Kant's view. He refers to it, and you can get by the Laws of Thought is reprinted with the original pagination as a Dover book, which I had great pleasure rereading recently. And here is what he had to say in response to Kant. To what final conclusions are we led then respecting the nature and extent of the scholastic logic? I think the following, that it is not a science, but a collection of scientific truths, too incomplete to form a system of themselves, and not sufficiently fundamental to serve as the foundation upon which a perfect system may rest. In sum, the work of creating a perfect logical system had to begin anew, and begin again using tools from mathematics. Boole's contribution to that work was what we now know as Boolean algebra, the invention of an algebraic system in which the mathematical objects treated are classes of things in an arbitrary universe of discourse, and the basic operations are the union, intersection, and complementation of classes. In Boolean algebra, showing the validity of the syllogism, all S are M, all M are P, therefore all S are P, can be reformulated as what Boole called an elimination problem. In his terminology, namely, to derive the equation, the intersection of S and not P equals 0. By the way, Boole invented the null class, or which he called the class empty, the class without beings. Intersection of S and not P is empty, which that's an equation which does not contain the variable m. Derive that from the intersection of S and not M is empty, and the intersection of M and not P is empty. So this is the same as all S or P, and this is the same as all S or M, and that's the same as all M or P. So to derive, validate Barbara, the famous first syllogism in the first figure, is to derive an equation not containing one letter from two equations which contain that letter. Although Aristotle's syllogistic dealt only with inferences from premises of the four forms I described, all S or P, some S or P, no S is P, and some S or not P, and not all S or P, premises containing two class names, or terms as they were called in English, and a conclusion containing two of those names, Boole's algebraic notation could symbolize premises and conclusions containing an arbitrary large finite number of terms and of arbitrary complexity. Boole also provided a general method, which you can find online. If you want a copy of this paper without complete footnotes, which it won't have for quite a while, I'll be glad to just email me. My email is on the Harvard webpage, and I'll be glad to send you a copy. So Boole's algebraic notation could symbolize premises and conclusions containing an arbitrary large finite number of terms and of arbitrary complexity. In addition, Boole provided a general method, a decision method he called it a general method, for determining which inferences are valid or invalid. And later versions of his rules are still used widely in a number of applications, particularly the design and simplification of electrical circuits. These achievements are, of course, well known. But there are a number of facts about Boole which are less well known. And even if they lead a little apart from the main subject of this talk, I cannot resist saying something about them. First, oops, I don't want that yet. First, the second of Boole's major works on logic, The Laws of Thought, contains even more than the development of Boolean algebra and Boole's general method. It closes, in fact, with substantial applications of Boole's methods to probability theory, applications that were followed 5 years later with the publication of a paper on the theory of probabilities that proved important inequalities, including one known to this day as Boole's inequality. An important inequality because it does not assume that the events that are partitioned are independent. And the generalizations of Boole's inequality by Bonferroni include one that is now famous as Bell's inequality, because of the use J.S. Bell made of it to establish non-locality in quantum mechanics. Bell did not know that it was a Bonferroni inequality. He proved it himself. What I particularly want to tell you about is something that I found very little reference to in the literature, although I'm sure Bertrand Russell, who is a great Boole admirer, knew it well. Namely that Boole pioneered the use of symbolic logic to analyze philosophical arguments. I'm referring to chapter 13 of the Laws of Thought, which both of you, those interested in logic and those in the history of philosophy, should read, in which Boole illustrates the wide range of subjects to which his logic can be applied by giving a very careful and very reasonable logical analysis of Spinoza's arguments for the existence and nature of God in the Ethics, as well as Samuel Clarke's arguments in his demonstration of the being and attributes of God. In my opinion, this ought to count as one of the first examples of analytic philosophy in one of its contemporary senses. Boole's conclusion in the last paragraph of that chapter is blunt. It is not possible, I think, to rise from the perusal of Clarke and Spinoza without a deep conviction of the futility of all endeavors to establish entirely a priori the existence of an infinite being, his attributes, and his relation to the universe. The fundamental principle of all such speculations, viz. That whatever we can clearly conceive must exist, fails to accomplish its end even when that truth is admitted. De Morgan, like Boole, summarily rejected the traditional idea that Aristotelian syllogistic was adequate for the analysis of all valid rules of inference, forms of inference. There's a story that I've often seen repeated, but I'm unable to find confirmed in De Morgan's published writings. Some authors say it's traditionally attributed to him, that De Morgan pointed out that nothing in traditional logic allows one to deduce all heads of horses or heads of animals from the premise all horses are animals. But whether De Morgan did use that particular example or not, he's emphatic that the logic used in mathematics is a relational logic, and that there was no traditional or contemporary, Boole's algebra also did not deal with relations, a formalization of reasoning with relations, two place and more predicates. As De Morgan did say in print, the algebraist was living in the higher atmosphere of syllogistic, he means logic, the unceasing composition of relations, before it was admitted that such higher atmosphere existed. He pointed out in this connection that mathematical statements are full of such relations, such as is less than, divides, let's see, not quite yet, such as less than, divides, is congruent to, etc. In 1860, just 6 years after the appearance of the Laws of Thought, De Morgan's syllabus of a proposed system of logic appeared. And although De Morgan did not have the mathematical powers of Boole, he did propose the earliest portions of relation algebra, which were taken up again by Tarski, by the way. 10 years later, Peirce made his first stab at a notation for quantification. Peirce made his first stab at a notation for quantification in 1870 in a paper called Description of a Notation for the Logic of Relatives. This is not to do with his in-laws. Relatif is the German word for relation, and Peirce imitated in English logic of relatives, meaning logic of relatifs. In 1879, Frege famously devised the first complete quantifier notation, of which more shortly, while Peirce and his students independently produced what is essentially today's quantifier notation, that is, notations for there is at least one x such that and every x is such that, in 1883. Peirce also developed and extended De Morgan's logic of relations to what we today know as first-order logic. That's, by the way, a Peircean name, although it's made popular, I think, by Hilbert and Ackermann, who called first-order logic restricted predicate calculus, paren, also known as first-order logic. That is the predicate calculus, including quantifiers over individuals in a non-empty domain, which can be arbitrary. But this was simply, first-order logic was simply referred to at the time, as by most logicians, as the Peirce-Schroeder logic of relatives. This version of first-order logic was made widely known in Volume 3 of Schroeder's Vorlesungen über die Algebra der Logik, lectures about the algebra of logic in 1885. Typo in my manuscript. At this point, it might be claimed the search for what Boole called a perfect system of logical inference was complete. There's that sequence. 1847, Boole's mathematical analysis of logic. 1854, Boole's The Laws of Thought. 1870, Peirce's first stab at a quantifier notation. 1879, Frege's Begriffsschrift, concept writing, which contains a complete quantifier notation. 1883, Peirce and his students produced what we today know as first-order logic. 1885, Schroeder's Algebra der Logik, Volume 3. Oops, I want to go back. But note, from 1854, when Boole declared that traditional logic is not a science, but a collection of scientific truths too incomplete to form a system, to 1879, when Frege published his Begriffsschrift, concept writing, was a mere 25 years. And from 1854 to the appearance of the Peirce-Schroeder version of first-order logic, just 31 years. Given the failure of even giants like Mill and Kant to question the completeness of Aristotelian logic, it is amazing how rapidly the radical views of Boole and De Morgan became accepted. It's as if they had but to shout, "The emperor has no clothes." To be fair, there was one great 17th century philosopher who realized the need for a real logical calculus, Leibniz. But there is an irony. In the article titled Leibniz's Influence on 19th Century Logic in the Stanford Encyclopedia of Philosophy, we read, "What are the connections to Leibniz's logic? Are there anticipations of the Boolean calculus in the work of Leibniz?" One of those authors looking for anticipations was Robert Leslie Ellis, who lived from 1817 to 1859, so he died just 2 years after the Laws of Thought, who edited Francis Bacon's Novum Organum in the works of Francis Bacon. During his editorial works, he found a parallel to Boole's law that A intersect A is A, which shocked people for some reason. And he writes, Mr. Boole's laws of thought contain the first development of ideas of which the germ is to be found in Bacon and Leibniz. To the latter, of whom the fundamental principle in logic, AA equals A, was known. As reference, he gave Erdmann's edition, which was only in 1840, of Leibniz's. Robert Harley, who was Boole's first biographer, discussed this information in a paper entitled Remarks on Boole's Mathematical Analysis of Logic. He did not find the quote at the place indicated by Ellis, but he found other relevant texts. About the significance of Ellis's remark, he wrote, Boole did not become aware of these anticipations by Leibniz until more than 12 months after the publication of the Laws of Thought, when they were pointed out to him by R. Leslie Ellis. But George Boole's widow, Mary Everest Boole, wrote that her husband, having been informed of Leibniz's anticipations of his own logic, felt, quotes, as if Leibniz had come and shaken hands with him across the centuries. Leibniz clearly had the project of a logical calculus in mind, but the 19th century logicians learned of this just too late for it to be an influence. And there's no evidence that Leibniz went very far in the direction of carrying out his project. The significance of Schroeder's book, you know, is that volume 3 made Peirce-Schroeder notation for quantifiers known to the whole logical world. It's the only notation either Löwenheim or Zermelo used in their famous papers. The question, does first-order logic really provide the perfect organon for deductive inference that Boole thought we should work towards? Well, some people think yes. The term Hilbert's thesis has been used for the idea that we do have a complete organon of deductive inference. Hilbert's thesis says yes. Nota bene, as Warren Goldfarb has pointed out, two important features distinguish Frege's approach to logic from the Boolean tradition. And this is important to understanding how they led to different programs. For Frege, the aim was not to produce an organon of valid reasoning about an arbitrary subject matter, as it was for Aristotle, and also for Boole, De Morgan, and Peirce, but to produce an ideal language in which all possible contents, Gedanken, could be expressed, and Frege's overriding preoccupation could be justified, namely to show that pure mathematics could be reduced to a pure abstract logic, what we would today call higher order logic. And thereby to show that, as Bolzano had already maintained, no appeal to spatiotemporal intuition was presupposed by arithmetic, including the arithmetic of real and complex numbers and the theory of functions. That the elimination of intuition Frege sought was specifically connected with spatiotemporal intuition is often missed today. It's stressed in a recent collection of essays by William Dimopoulos on logicism. In another respect, however, Frege resembled Aristotle, but not the Booleans. For Aristotle, the notion of validity was a primitive one, whereas for the Booleans, a valid equation in Boolean algebra or valid formula in the calculus of relatives or predicate logic is simply one that becomes a true statement upon the substitution of any class names whatsoever for its predicate variables and the choice of any universe of discourse as the domain over which the quantifiers range. In other words, a formula is conceived of as having indefinitely many interpretations. And a valid formula is one which is true no matter which interpretation we choose. This is now called a semantic notion of validity. For Frege, his ideal language had but only one interpretation of interest, the one he had in mind. And if his purposes required that his language be higher order, as he believed, then singling out for attention just the first order part was likewise of no interest. As far as I've been able to determine, the first published complete method of deduction in just first order logic was Peirce's diagrammatic method in his 1903 existential graphs. In sum, because he had no interest in reinterpreting his logical symbolism, Frege had no interest in developing such a concept as the concept of different models of any part of his Begriffsschrift. Nor, as I just said, did he have any interest in first-order logic as such. Put these two disinterests together, and you see it's no accident that the first major result in model theory, the Skolem-Löwenheim theorem, that every formula in first-order logic that is satisfiable in some universe of discourse is satisfiable in some finite or countably infinite universe was not proved by someone influenced by Frege's work. The first proof of that theorem, Löwenheim's, was proved using Peirce-Schroeder notation and refers to first-order logic as the calculus of relatives, as one would expect. No one other than Frege used Frege's notation in a published paper, to my knowledge. Nor is it the case that the use of quantifiers in the 20th century was due to Frege, although you can find statements to the contrary without any supporting evidence everywhere. On the other hand, although Peirce shared with Frege an interest in the foundations of arithmetic, far from wanting to show that arithmetic needed no appeals to spatio-temporal intuition, he wished to show that logic itself was essentially reasoning with diagrams and hence a form of geometrical reasoning. Important programs in logic were stimulated by two absolutely contradictory philosophical theses. That is why his proof procedure for first-order logic, I mean the Peirce's diagrammatic procedure, which is actually quite elegant and surprisingly quick to find proofs in. In fact, when you draw the diagrams, the proofs just seem to flow from themselves, is geometrical. Thus, if Frege could not have become the father of model theory, neither could Peirce have become the father of logicism. After these developments, although there are let me see what's coming next. There are various systems that extend first-order logic, including not only the higher-order logics of Frege and Russell Whitehead, but also modal logic, tense logics, deontic logics, Hintke's independence-friendly logic, etc., etc. By and large, the majority view now seems to be that the real organon of methods of deduction in science is exactly first-order logic. The search for a system more perfect, to use Boole's term, than first-order logic seems to have been abandoned. Indeed, after the remarkable accomplishments during the 31 years that began with the publication of the Laws of Thought in 1854 and saw the publication of Frege's Begriffsschrift in 1879 and the dissemination of Peirce's notation for first-order logic by Schroeder in 1885, it might well have seemed that little more remained to be done. But on the contrary, the 20th century was to expand the domain of mathematical logic much, much farther. Already in 1893 and 1903, the years of publication of the 2 volumes of his Fundamental Laws of Arithmetic, Frege launched the Logicis program, the program of reducing all of mathematics to higher-order logic. And although his own attempt to complete that program was shown to be inconsistent by Russell, the latter, unlike Frege himself, repaired and extended logicism with profound effects on 20th century logic. Besides the Boolean stream, culminating, by the way, if Frege himself went back to I think Paul Benasser knows more about this than I, went back to a geometrical foundation for arithmetic after the discovery of the Russell contradiction. And if the logical word had followed him and Peirce, we would not have logicism. But fortunately, Russell did not give up on logicism. Besides the Boolean stream, culminating, as I've described, with Peirce and Schroeder, and the logicis stream, beginning with Frege, a third stream, the Hilbertian stream appeared and played a large role in the 20th century, leading to the developments associated with the name of Kurt Gödel, as well as with those associated with the name of Alfred Tarski. One could devote a volume at least to logicism and its variants, including a recent one called neologicism due to Crispin Wright, but I shall focus on the Hilbertian stream because that is the one that led to the work of Gödel, Alonzo Church, Alan Turing, and flowing from that, modern computer science, with its importance in contemporary life. To those students among you who want to know more about logicism, I recommend William Dimopoulos' brilliant collection of essays, Logicism and Its Philosophical Legacy. As I have before, I will try to be as non-technical as possible. My aim in this talk is not to describe technical methods or results, but to understand the motivations behind the remarkable developments I will be talking about. So, David Hilbert. Hilbert, who lived from 1862 to 1943, was not just one of the greatest mathematicians of his era, but also among those whose work spanned the most fields, and at the turn of the century, perhaps the most influential. As one author has put it, Hilbert's address of 1900 to the International Congress of Mathematicians in Paris is perhaps the most influential speech ever given to mathematicians by a mathematician, or given about mathematics. Almost 6 decades after it was given, my own mathematical life was shaped by that address. In 1959, the fact that a problem on Hilbert's list, the 10th, was to find an algorithm that decides whether or not an arbitrary Diophantine equation has a solution, inspired Martin Davis and myself to start looking for a negative solution, that is a proof that no such algorithm can exist. Joining our efforts with Julia Robinson, we came close to a solution, but not all the way. And the last piece was provided by the Russian mathematician Yuri Matyasevich in 1970. The result is often referred to as the Matyasevich MRDP theorem, or simply the MRDP theorem. Matyasevich, Robinson, Davis, Putnam. I doubt that Davis and I would have chosen that particular problem to work on if it hadn't been on Hilbert's list. In a word, Hilbert pioneered the field called metamathematics. Although Alfred Tarski was later to broaden the scope of mathematics, metamathematics, both with respect to the questions to be investigated and with respect to the methods to be used, for Hilbert, metamathematics had 2 grand objectives. One, to find consistency proofs. To prove the consistency of arithmetic, analysis, and at the most ambitious extreme, the whole of extant mathematics as formalized by Russell and Whitehead in Principia Mathematica. And second, to find decision methods for determining the truth or falsity of statements in the various branches of mathematics. At one time he believed that a decision method for the whole of mathematics should be possible. Such a program is already in evidence in lectures published by Hilbert from 1900 on. The second problem on Hilbert's famous list was, quotes, prove that the axioms of arithmetic, and arithmetic included analysis in that lecture, prove that the axioms of arithmetic are consistent. But it assumed its mature form only in 1921, 1922. Before that, between 1913 and 1917, Hilbert and his students studied Principia intensively. In fact, just before the outbreak of World War I, Hilbert planned to invite Russell to come lecture in Göttingen, but the outbreak of the war put paid to that idea. And Hilbert flirted with logicism. So as I say it here, so metamathematics had 2 objectives already in 1900, to find consistency proofs, but not at that point finitist proofs, for at least arithmetic and analysis, and to find decision methods, e.g. the 10th problem that Davis, Robinson and I worked on. But the correctness of classical mathematics itself, and indeed of classical logic as well, had been questioned by Brouwer, the father of intuitionism, from 1908 on. And Brouwer had become a severe critic of Hilbert's still developing views on the foundations of mathematics. Related criticisms were made by Poincaré and by Hermann Weyl, a former Hilbert student, who defected to a view related to, if not as extreme as, Brouwer's. Semantical consistency proofs and proofs that assume higher order logic were seen as simply question begging. Brouwer's views, however, presupposed an appeal to intuition in a sense peculiar to his own thinking, not Kant's spatio-temporal intuition, that Hilbert found unacceptable. Hilbert came to the conclusions that 1, classical mathematics needs no philosophical interpretation at all. It should be treated as a game with uninterpreted symbols, a mere formal system. 2, the justification needed for classical mathematics is simply a proof of its consistency. But that proof, these are not restrictions on metamathematics, please note, but they're restrictions on mathematics in the usual sense. 3, that proof must use means that not even an intuitionist could object to. The use of reductio ad absurdum, that is proving a statement by assuming the opposite and deriving a contradiction, is only to be allowed for negative propositions, not for existent statements. The law of the excluded middle is only valid for decidable propositions, etc. These restrictions are not to be imposed on ordinary mathematics in contradistinction to Brouwer's view, which we should give up ordinary mathematics if it doesn't fit his views, but they are to be rigorously followed in metamathematics. This Hilbertian program, and not the Aristotelian program of codifying deduction, or even the Frege-Russell program of showing that mathematics could be reduced to higher order logic, is what drove logic on and on. Logic became in large part metamathematics, although after Tarski in a much larger sense than Hilbert had envisaged. This Hilbert program had a number of presuppositions, namely, these are presuppositions and limitations of the Hilbert program. 1, if mathematics as a whole and each of its various branches are to be treated as games with symbols, then mathematics needs to be completely formalized. But in Hilbert's view, that had already been taken care of. Principia Mathematica had shown that this could be done. And of course, it could be done in other ways as well, as Hilbert knew, for example, Zamilo's set theory. 2, of course, logic too must be completely formalized, but that had already been done both by Peirce Schroeder, and Hilbert expresses great admiration for Peirce, by the way. The idea that nothing happened in logic before Frege seems to have come either from Drebin or from Heijenoort, and I've never known which influenced the other, but it's now spread like a cancer throughout this history of 19th century mathematics. But logic, so you can understand Hilbert's great admiration for Russell, because Russell had done a lot of work, spade work, that Hilbert thought had to be done before the logicism program really made sense. The logicism program, the formalist program made sense. The formalist program assumed that there was a formalization of mathematics as a whole and of logic as a whole to be proved consistent. But that had been done. Both by Peirce Schroeder and by Frege, as Hilbert and Ackermann point out in their great 1928 textbook, Principles of Mathematical Logic. 3, in the light of 1 and 2, the question of the consistency of geometry or arithmetic or set theory is a well-defined mathematical question. It's just a question of whether a given game with meaningless symbols, a certain game with meaningless symbols, or something that can be so regarded, is or is not such that one can obtain certain undesirable positions by following the rules. For example, can one be forced to print out or write down 1 equals 0? Can one be forced to write down or print out something in the form P and not P by the rules? An important limitation in Hilbert's own thinking is he never considers, until Gödel's results force him to do so, the possibility that mathematics cannot be proved consistent by the finitest means he allowed. And by the, oh no, I don't think they can be. I don't think Gödel's incompleteness terms prove that cannot be done. But that I will leave as a dangler for the question period. A negative solution to a decision problem, such as the negative solution obtained by Davis, Robinson, Maciejewicz, and myself to his 10th problem, is never envisaged by Hilbert. And it's not clear that he would accept the now standard view. I doubt that he would, that the results of Gödel, Church, Turing, etc., have shown that a consistency proof of the kind he sought, or even a decision method of the kind he sought, is impossible. But as it turned out, The course of mathematical logic after Hilbert turned sharply, though not exclusively, on such negative solutions and their interpretation. To explain this, we need to turn to the work of Gödel and to Church's thesis, and that, I'm afraid, will use up the rest of my time. So I have here a list of 11 fabulous years of Gödel. Not that he didn't do anything after, but these are his miraculous decade or decade plus a year. 1929, PhD thesis at Vienna, completeness theorem for first-order logic. Actually published in 30, the year after. 1931, the famous incompleteness theorems. 1934, his Princeton lectures on recursive functions, where he defines a class of general recursive functions now identified with the computable functions. And 1940, consistency of the continuum hypothesis and the axiom of choice with the axioms of set theory. I'll pause for a moment to let you look at that list. It's really Gödel's first world-famous results, contained in his 1929 doctoral dissertation at the University of Vienna, was not in the area of Hilbertian metamathematics at all. It was neither a consistency proof nor a decision method, but was a fundamental result of what later became called model theory, namely that every formula of first-order predicate calculus that cannot be disproved from the axioms, that is, every formula P such that not P isn't a theorem of first-order logic, has a model. That is, an interpretation of its predicate letters over some non-empty domains such that it comes out true under that interpretation. Since it's easy to show, assuming classical logic, that the axioms of first-order logic are valid, and that the rules of inference are likewise valid, we know that first-order logic is sound. All its theorems are valid. Gödel's result shows that all the formulas that aren't theorems aren't valid. So first-order logic is complete. Its axioms and rules suffice to prove every valid formula. Hence the theorem is called Gödel's completeness theorem. Gödel's proof of his theorem shows that first-order logic has an important property called compactness, but I will not explain that here. Only 2 years later, 1931, in a paper titled On Formally Undecidable Sentences in Principia Mathematica and Related Systems 1, there is no 2, by the way. I wonder what he planned to publish in 2. Gödel did turn to metamathematics in Hilbert's sense and proved 2 theorems that are widely regarded as having put paid to Hilbert's program. The famous paper showed, as very likely you all know, that there are sentences of piano arithmetic. In fact, sentences of the form there is an n such that f of n equals 0, where f is an effectively calculable function, in fact a primitive recursive function on the natural numbers, such that neither the sentence nor its negation, neither there is an n such that f of n is 0, nor there does not exist an n such that f of n equals 0, can be proved in Principia unless Principia is inconsistent. What makes the pill bitter, this is the significance of the word "and related systems" in the title of the paper, is that the same proof can be given in any system that contains just a small fragment of the theorems of arithmetic, not just Principia. In short, no consistent system with a finite number of axioms can be complete, in the sense providing a proof of this or disproof of every true arithmetic sentence. For either it must fail to contain all of the small fragment of the theorems of arithmetic I just alluded to, in which case it's obviously incomplete, or the Gödel theorem, technically Gödel's first incompleteness theorem, implies that it's incomplete. In either case, it's incomplete. But the pill gets more bitter still. The same paper contains a second incompleteness theorem, namely that one of the sentences that a system that contains even the small fragment of the theorems of arithmetic in question cannot prove is a number theoretic equivalent of the syntactic statement, the metamathematical statement in precisely Hilbert's sense, that the system is consistent. More precisely, Gödel showed that a system cannot prove its own consistency unless it is inconsistent. So if we assume that finitist consistency proofs can be formalized in some one acceptable system, which, by the way, I don't think Hilbert ever believes, then that system must be one whose consistency cannot be proved finitistically. And this is what most logicians believe crushes Hilbert's hope for an uncontroversial, uncontrovertible, and uncontroversial finitist consistency proof for mathematics. If somebody wants me to ask what about the Gensen proof, I'll be happy to say something about that in the discussion. Okay, not there. Gödel went on to more wonderful achievements. In that same decade in which he proved the incompleteness theorems, the 30s of the 20th century, he was to prove that the axiom of choice is consistent with the other axioms of existing Zermelo-Fraenkel set theory, unless they are themselves inconsistent, and then 2 years later to do the same with the continuum hypothesis. In 1963, Paul Cohen showed that the negations of these two statements are also consistent with present-day set theory. And Gödel also pioneered what became known as recursive function theory, today often referred to as the theory of computable functions. Yes, he did that too. Gödel and computable functions. I don't have a PowerPoint on this part. The textbook from which I and many others learned recursion theory was Kleeni's Introduction to Mathematics. From that volume, we learned that, quotes, the characterization of all, quotes, recursive functions, close quotes, was accomplished in the definition of general recursive function by Gödel in 1934, who built on a suggestion of Erbrand. Although Gödel did not himself propose a thesis or hypothesis that the general recursive functions are all the functions that are effectively computable, that was to be done by Church and by Turing 2 years later, the Gödel definition was the first mathematical definition of the class of computable functions. To this day, the fact that such seemingly different definitions of computable function as Gödel's, generalizing Erbrand's generalization of previous notions of recursive function, Emil Post, generalizing the notion of a derivation from axioms, Turing's analyzing and stripping down to its essentials the notion of a computer, and Church's lambda calculi all yield the same class of functions is a powerful piece of evidence for the Church-Turing thesis that the notion of computability has now been successfully formalized. If Hilbert was never convinced that Gödel's incompleteness theorem was fatal to his program, it is, I conjecture, because he was never convinced that the Church-Turing thesis was true. But neither he nor anyone else has produced a convincing example of something that is intuitively a method of calculation that is not reproducible by a Turing machine, or a function whose values we can effectively calculate that is not general recursive. What I can and will do in closing is just to mention the two largest areas that I left out. The first of these is the achievement of Tarski, by which I mean not only the formalization of the concept of truth in formalized languages, an achievement whose significance for philosophy is still under intensive exploration and debate, but also the impetus he gave to model theory, which is now one of the main areas of research in mathematical logic. The second is the achievement of many different workers in modern set theory, including Hugh Wooden, who gave up my predecessor in this lecture series, who is trying to find ways to motivate the adoption of powerful new axioms for set theory to tell us whether we should believe or disbelieve the continuum hypothesis. And my own student, Harvey Friedman, who in addition to many other achievements is showing us how to find sentences that are, one, not decidable in the present-day set theory, and that two, address natural mathematical questions. I think one can draw two morals from the story of how logic ceased to be a museum piece. An obvious one is that one should never say of a field that of inquiry what Kant said of logic, never say it's closed and completed. Good pragmatist moral. Don't block the paths of inquiry in Peircean language. A second is one should never suppose that we can delimit once and for all what the subject matter of a field is. A moral that I suggest applies to philosophy too, and not just to logic. For more than 2,000 years, it seemed clear that syllogisms were the subject matter of logic, and a little bit of propositional calculus, disjunctive syllogisms, hypothetical syllogisms, and so on. Today, the subject matter includes mathematics as a whole, computer science, mathematical linguistics, which I could have mentioned earlier, and still more. Who knows what it may include tomorrow? Thank you.
But continue to rate. I'll note. Great.
Thanks for this sculpture history. It's been great. When you spoke of the earlier work of Boole and folks like that, and trying to determine whether logic was an organon, what exactly did you mean by that?
Oh, I'm
a theory of science.
I take it that, I use organon, of course, it's Bacon's term, but I take it that in Bacon's sense, and I think Bacon saw Aristotle that way, Aristotle didn't think he had an organon of all deductive inference, at least, I think he launched a program which the Stoics also saw themselves as participating in, creating an organon of deductive logic, one that really pretty much perished when Stoic logic was lost. And I see that, and I take it that Boole's remark that what traditional logic, contrary to Kant, is not a science and not even it's scientific statements, but it's not even enough to be the foundation of an organon in that sense. But this is reopening the program of let's get something, say, about which something like the Hilbert's thesis could at least be plausible. Hilbert's thesis is the thesis that the organon program has been completed, and look and behold, it's first-order logic. I'm not wholly convinced, but it may be that it's a good enough approximation.
Rob.
Hi. I have a very general question, which is basically, what do you think is the relationship between logic and philosophy? I mean, the way that I would make that more specific, for instance, is, and particularly, what do you think we've learned about that in light of the story that you just told about the history of logic's development?
Well, I want first say that that's not my topic today. So I mean, it's a wonderful topic, but it's not my topic today. But I see a note of tragedy in Russell's very short intellectual autobiography. I mean, very short because he published a whole volume of autobiography. So when he came to his Schildt volume, the Library of Living Philosophers volume, Russell just has a very short intellectual autobiography. And when he says that, well, you know, so far it hasn't turned out that the new logic has solved the great philosophical problem, but I still have my hopes. And I think we now, you know, and against that, I was mentioning to the graduate students I had lunch with that Etienne Gilson, in his William James lectures, The Unity of Philosophical Experience, describes how in the Middle Ages, a number of philosophers thought that scholastic logic would solve the problem of the existence of, or non-existence, real existence or non-real existence of universals. And the irony of that, I must say, I didn't read every word of Justin's lectures, but I get I read the end, which is wonderful. And the irony of Gilson's history is he sees the unity of philosophical experiences. Philosophers keep making the same mistake, namely hoping that some other subject in philosophy will solve all their problems. But I also like Gilson's sentence close to the end of his lecture that philosophy always buries its undertakers. I know I'm ducking that question.
Young man there.
This is a pretty open-ended question, but you gave a remarkable one-hour recap of the history of logic. What do you think about logic as a subject today, and maybe what direction it will head, and maybe what do you think what direction it should head?
Well, I'm an enthusiast for Hugh Wooden's program, and I'm optimistic that something will result from it. I mean, I have a strong tendency to disbelieve the continuum hypothesis. I think most workers in that area now think that the ordinary continuum hypothesis, that 2 to the aleph null is not aleph 1. But I hope we learn much more about what is likely the case with way up there. But there are huge philosophical questions that remain. But I think that Gödel's belief that there might be additional axioms that will become evident, although I don't share the view that every mathematical question is such that will be eventually solved by new axioms becoming evident. At least with respect to the continuum hypothesis, I am optimistic, and I think that's fantastic work. And I'm very proud to be in the same series as you, Wooden. And I think that the way I see my students, Harvey Friedman's work, not just valuable, it would be what he's trying to do is, of course, I say, to find undecided Gödelian sentences that can be shown by Gödelian techniques to be undecidable that have real mathematical interest. But that's a fairly narrow program because its aims really is kind of trying to persuade philosophy, math departments not to look down on logic. But I think there's more that results from what he's doing. I think what he's already shown is that the axioms of set theory are enormously rich in arithmetic consequences. There is a field waiting to be created, just as this was not obvious a priori that the calculus would be the instrument for moving number theory ahead. And yet analytic number theory turned out to be such an enormously rich tool. And it was not obvious, by the way, that category theory would contribute to the solution of the Fermat problem, which it did. I mean, never mind the fact there are various arguments that the category theory can all be coded out of it. I believe that. But I also believe you would never, if somebody ever goes, first of all, maybe that no one will ever have the Sitzfleisch. And secondly, it was how it was discovered. Here, by the way, Harvey is a reactionary. He's on the side says, well, we could have dispensed with category theory. No interest in him philosophically that a non-standard way of thinking was the route to discovery. And so I think that without trying to predict what the next power grab by logic will be, because I'm describing two huge power grabs. Mathematics is saying the mathematical investigation of mathematics as a whole is part of logic. Right. And that has proved enormously rich. I don't know what the next power grab will be, but already with the power grab we've seen. But I close a sentence about, if I didn't close that sentence before about Harvey, what I'm saying is there's a field waiting to be created. In analogy with analytic number theory or category theoretic number theory, there's a field of set theoretic number theory which ought to exist. And I see Harvey's work as the first steps, because we don't know how to use all that excess information about the natural numbers that's quoted in Zimmermann-Fraenkel set theory. And that fact that there is enormous information about the natural numbers, they're waiting to be drawn out, is for me a pointer. Excelsior.
Other student questions? Yes.
You mentioned towards the end, you talked about the church Turing thesis, and you mentioned that it sounded as if Hilbert's sort of system would sort of go through it. He would reject the church Turing thesis, and that would somehow have recovered the system. What does it mean exactly to reject the church Turing thesis, and sort of how would that?
Well, I'll duck that a bit, but I will say, because but I will say something on why I think he was never convinced that the incompleteness theorem for Page was programming. The reason I think he probably also rejected the church Turing thesis is that he never really, you might think, he might have had hope, for reasons I'll mention in a moment, he might have had hope that the consistency programs could somehow go forward. But he never admits even that the program of looking for decision theorems has been killed by Gödel's work. And the only reason I can think of for not thinking that what Gödel showed kills that program would be that he wasn't convinced of the church Turing thesis. Now, as I say, this is speculative, because I'm inferring from the fact that he never said that he'd given up on the decision method program. that he in fact found, which is possibly wrong. So I really have not much more to say on that. But I mentioned the Gensen proof. Gensen proved the consistency of first order number theory by finiteness means. Let me repeat that. Gensen proved the consistency of first order number theory by finiteness means. That's widely unappreciated because very few people know both, because very few people know both Gensen's proof and what finitism was. So it sounds, yeah, how come, but doesn't the Gensen proof use induction on a well-ordering of transfinite length? How can that be finitus? Well, first of all, induction, say, on omega times 2 is already transfinite. Induction on recursive well-ordering, so ordered type omega times 2, is unquestionably constructive. Now, the reason, so the problem with epsilon zero induction is slightly more tricky. Induction on the induction schema, or any instance of the induction schema, on well orderings of, say, omega times 2, or omega times omega, or omega cubed, these forms of the induction schema can be derived in intuitionist arithmetic. They're perfectly constructed proofs. Induction on a recursive well ordering, a primitive recursive well ordering of order type epsilon 0 cannot be derived in piano arithmetic, but induction on any initial segment of an epsilon 0 ordering can be derived in first order arithmetic. And moreover, that there's a proof, proof that satisfies all the conditions for finiteness proof of induction up to alpha for any alpha less than epsilon 0 is itself a theorem of intuitionist arithmetic. To get epsilon 0 induction, you need one application of the following reflection scheme. If there's a proof of induction, of the induction schema, or your favorite instance, whatever instance is in question, if there's a proof of induction with the induction schema with that predicate up to alpha I, for each I in a series of ordinals, alpha 1, alpha 2, alpha 3, that approaches epsilon 0 as a limit, if there's a proof, if there's provably a finite proof of induction up to alpha I, for each alpha I, then that counts as a finiteness proof that for all I, induction is valid up to alpha I, which is epsilon 0 induction. Now, at this point, you begin to see why it's not clear, in fact, Hilbert, that finiteness proofs are indeed all proofs in one formal system. You might say, well, just formalize finiteness reading. You have one formal system, and then apply Gödel's theorem to it. But finiteness reasoning includes reflection principles. Forget ordinal. Just the reflection principle is for each n there's a finiteness proof of f of n. Then that's a finiteness proof for all, and you can prove that finiteistically, then that's a finiteness proof for all n f of n. That cannot be schematized. Then you get into sort of Turing's work on hierarchies of languages where you use stronger and stronger reflection principles. It's not at all something we know that finiteness proof is something that can be captured by a single formal system which can apply to Gödel theorem. On the other hand, our mathematical experience, and I've given PhDs to proof theorists, and I've tried myself to extend Gensen type methods up to ramified analysis. There's no indication that Gensen type proofs will get you up to all of analysis. But at the moment, the pessimism about the Hilbert program is justified. But it's not the idea that the Gödel theorems put pay to it. I'm saying it's not justified. And that's something in which, by the way, if you're looking for a PhD thesis in philosophy of mathematics, there's lots to think about.
Hi, Dr. Putnam. I was wondering if you could talk a little bit about the relationship between the development of first-order logic and epistemological skepticism.
I think the epistemological skepticism with respect to, I mean, I'm not a historian of philosophy, I'm an amateur historian of philosophy. I love the history, but I never claim to be professional. But skepticism with respect to the question of whether logic itself is justified becomes a philosophical question for the first time, to my knowledge, early in the 19th century. And especially among post-Kantians, post-Kantian idealists, Hegelians, and so on. For the first time, they say, well, we don't have a justification for logic. But I don't think that skepticism ever shows up very much in English philosophy, English language philosophers, although there are a lot of English language idealists that I don't know. And I don't think that it was influenced by first-order logic. It was already, Aristotelian logic was enough. They were already asking, what's the justification of the excluded middle? What's the justification of the principle of contradiction, and so on. The question, it's not, because you don't need, you only need to know, because once you question the excluded middle and principle of not contradiction, you don't need to ask how much more there is. Those have not been justified.
Let's open up the question more, Jonathan.
I was wondering, on a more personal note, if you'd be willing to share a little bit about your experience at Penn, particularly tell us about being the sole member of the Philomathean Society.
I don't think I could have been the sole member because somebody had to admit me to membership. I didn't just walk into the, I know I didn't just walk into the Philo group and announce the Philomathean Society is open for business. I remember a small number of others. Yes, I have a feeling here and there, at least maybe 6 of us or so. And I don't remember who they were. They were not among my best friends. That was my own project. Yeah.
Okay. So more generally now? Michael.
You said at one point, and I couldn't tell if you endorsed, something like first-order logic is sufficient for understanding all of deduction in natural sciences.
Well, that's Hilbert's thesis.
Hilbert's thesis, yes. Yeah. But you sort of sounded like maybe you endorsed it. I just wondered, but more generally, what do you think the status of that thesis is?
Well, there is a PhD thesis on it I found online, which I copied down online by a student of George Boulous's. If you email me, I can send you the reference, which I think is skeptical. I guess it's hard to say. If you say, well, why not second-order logic? I mean, there I think, although I think it's skeptical to supply, they reply that second-order logic is not an organon, because we don't have, you can't have a complete set of axioms for second-order logic. And when we reason in second-order logic, it's usually it means deduction in Henkin models, which looks like first-order logic in disguise. Now, but on the other hand, on the other side, I don't think it certainly doesn't capture all of the inferences regarding reasonable deductive inferences in ordinary language, in particular ones involving branching quantifiers. Or Boulous's plural quantification. It seems to me, to say that, well, when I say some Republicans at the party talked only to each other. It doesn't sound as I'm saying there's a set, et cetera, et cetera, et cetera. Now, what may be true is that we can, by adding some other theory like set theory, or quantification over possible worlds, depending on what the case may be, by adding some bit of theory, we can reformulate all the inferences we accept as valid as inferences from the original premises plus the axioms of this bit of theory. That sounds a bit like cheating. I mean, it shows something about first-order logic. That is, that Hilbert's thesis is at least tenable. But
It seems like it shows it's important.
no, it's certainly
Not that it's enormous.
It shows how much, yeah, the fact that it's tenable or can be, shows that how much we've accomplished.
There was a question there.
Yeah, what did you mean when you said that you're talking about Friedman's work, and you mentioned arithmeticity and the applications of, I don't know, the applications of, we're trying to say that large cardinals could be, theory of large cardinals could be applied to arithmeticity?
Yeah.
I mean, what do you mean? I mean, you know, you can apply the axiom of choice to arithmeticity by saying that, for instance, the existence of non-measurable sets in R is, you know, strictly speaking, an arithmetic constant.
No. The point of Friedman's publications and FOM, doing the work he's working now, is to show that combinatorial statements that at least look sort of like high-powered versions of Ramsey's theorem, combinatorial statements, which on the face of them have nothing to do with large cardinals, are applied by large cardinals.
I see. So not arithmetic, like combinatorial.
No, they're generally, but they are mathematical statements, some of which are in fact arithmetical statements. I don't know about large cardinals and arithmetical statements, so I bet Harvey could give you examples.
Okay.
But sort of the mathematical content or the combinatorial content of the set theory is enormous, and we don't know how to exploit that.
Zoltan.
I know you didn't want to go beyond Tarski, or not even to Tarski, because you didn't have time. But supposing you had another lecture, so then let's not talk about Tarski, important man, but I wanted to ask, would you include anything like quantum logics and all these many-valued logics, many kinds of logics, that looks like the original Boolean framework erodes into lattices that are not distributive, not even modular, orthomodular, and so forth. So is there any limit to what kind of things you will include in logic, or anything goes?
Well, the study of distributive lattices, if you want to call it part of logic, call it part of logic. But I have a paper in my new book explaining why quantum logic, of which I was guilty, was a mistake, called The Curious Story of Quantum Logic.
Right.
And I invite people to read it. But it's then trying to, on the other hand, say, well, study of logic on Hilbert spaces isn't logic. Well, Hilbert thought it was, and that's...
Or Neumann thought.
Yeah, the Neumann. Yeah, well, you can call it logic, but I don't think it has... It's at least any breakthroughs in the understanding of quantum mechanics. What I think was a mistake was not investigating this funny logical system, or not, but the idea that it wasn't this non-standard logic was, in some sense, as I put it, the logic of the world. I was guided by a false analogy with geometry. I mean, Quine did teach me to very much distrust the claim that anything is a priori, and I am grateful to him for that. Well, I think that's but logic is pretty safe. I mean, provisionally a priori. I don't believe in any absolute a priori epistemically, but I think there are things that are provisionally a priori. Classical logic is one of them.
Yes, there.
I was wondering if you could sort of comment on the contribution of Wittgenstein to logic. I know you probably didn't have time to go into that, but I feel like it relates to an earlier question as to taking logic and applying it to problems of philosophy. And I was wondering if you thought that, I mean, I could see how that could almost be like another sort of Kantian attempt to just like bury logic in a way. I was wondering what your opinion was.
I'm sorry, I didn't hear.
Maybe you could stand up and actually...
Even with my hearing aid.
If you could comment on the contributions of Wittgenstein to like logic.
I don't see Wittgenstein making a contribution to logic. I mean, he's credited, one of the people who's credited with truth tables. But I've never seen Boole credited, but Boole's law of 0 and 1, which is that a Boolean formula is valid just in case the corresponding state, well, we would put it in, take the corresponding state and reinterpret as the Boolean algebra as an algebra over integers, and substitute 0 and 1 for errors in all possible ways. and do mod 2. Mod 2 is not an expression Boole had, but basically that's one of Boole's methods. And that seems to me to amount to truth tables. What's the difference between substituting t's and f's in all possible ways and substituting ones and zeros in all possible ways?
Question. You said dismissing everything that is a priori, would that include?
Yeah, I'm putting closer.
Yeah. Thank you. It's wonderful to hear you. You said that about dismissing everything that is a priori. Would you include reason in that? And if that is so, then why do different people have different reasons for it?
Well, I don't say what I reject is the idea that there is such a thing as that there is any clear status, which what we might call being apodictically a priori. I believe there are. I believe in what I've called what's the terminology there? Basically, there are some statements a priori relative to a body of knowledge, and the question: could there be any conceivable circumstance in which we would revise them? I think there's no clear sense. We can say now that we cannot say, for example, I don't see any convincing way we see how, even though I tried myself in quantum logic, I don't see any way in which I cannot say any way in which the distributive law would be false. If P and Q are R, then PQ or PR. I thought quantum mechanics was an example. I now think that was a mistake. So now my position is, as before, that I can give kind of minimal sense to the idea that even the distributive law might be self, in the sense that sort of the weak analogy that since we've been mistaken about things about which we were equally sure, for example, the impossibility, the parallels postulate, so we don't have a guarantee that something like that won't turn up here. But so what? I'm trying to say that you can really support a doubt only by showing of a proposition, only by showing a way it could be false. And for me, that's enough. We don't need to. In other words, I think the search for the absolutely a priori, as opposed to the search for what's a priori as far as we can tell, is a waste of time.
Other questions? Yes.
Yeah, so I just wanted to invite you, so you drew a comparison with, you started off with talking about Aristotle's ergonon and Stoic syllogistic. But one thing that's sort of salient there is that the Stoic and Aristotelian notions of validity are not just truth preservation, right? They require some sort of explanatory connection. The Stoic notion is explicitly non-monotonic, maybe even anti-monotonic.
Yeah.
So do you think that there was a large shift in the conception of validity between, obviously something changed between them and Boole?
Well, I may say unfairly. What I say here is I think that Aristotle didn't feel a need to really define logical consequence. That may be unfair. But the idea that there are two ways of conceiving it is, I think, follows really around 1900 when you begin to contrast the Boolean way.
You could actually get a version of this in the Stoics, where they have a definition of validity in terms of incompatibility of the premise and conclusion. They don't really quite say what that is.
Yeah. The problem is there's so little left. That's why I say they were really dark ages.
Max. I'm sorry. Yes, Alan.
This was a question, sort of a pedagogical question about how we should teach history of analytic philosophy. So you've made the sort of provocative suggestion that Boole should really be placed at the beginning of the story. And in my experience, he isn't usually. And I was wondering if that's just because of sort of inherent difficulties in the text, or if you think it's just a sort of historical error in a way that we should correct at this point and start reading Boole in the sort of standard history.
Well, I think what should take chapter 13 out of the laws of thought. You can read it tonight. I think Russell would have totally agreed with what I said. Russell had read Boole. I think we don't read the laws of thought. What is it? Boolean. I need to read about Boolean algebra. probabilists read I think it's the chapters after chapter 13. There's wonderful stuff on probability theory there. No, I think it's simple ignorance. I was amazed. I'd never read it before. When I was preparing this lecture, I got up my laws of thought, went on reading. What? You're going to do a logical analysis of Spinoza's premises? What? I've taught, just directed at least one dissertation, maybe two on Spinoza. I never knew, and I didn't know this.
I just wanted to follow up. Do you have a sort of sociological or historical explanation for this? I mean, do you think it's was it historians of analytic philosophy at Harvard that did this, or
no, not with. Well, I think von Heyenard, I don't know who stimulated von Heyenard, Reb, and Quine had the story. Really, nothing happened in logic before Frege, and I don't know, which is not Hilbert and Ackermann.
So you think it might have started with them?
I think so. Suddenly began, well, I think it's partly when we realized what a great philosopher Frege was, then the fan club started. It's easy to be a fan of Frege. But fans get out of control.
It's Frege hooligan.
Exactly. That's what I'm saying. Frege hooligan.
Man for fanatic.
Of course, Shannon didn't forget Boole, and Tarski says wonderful things about Peirce.
Okay. Yes.
Dr. Putnam, you mentioned the quote about philosophy always being its undertakers.
Yeah.
So I take it you have in mind in Russell's and Wittgenstein's generation logic or logicians as the undertakers, or at least these fans of logic, right? Wittgenstein thinking that logical analysis will yield solutions to all the problems of philosophy.
Come on, get off. Ignore that. Ignore.
So my suspicion is that you see these undertakers, at the beginning of the 20th century as these fans of logic, these fans of Frege, and maybe today as sort of like natural science worshippers. Is that suspicion correct, or do you want to correct it?
Well, as I say, I'm not a professor historian. My sociology is largely limited to what I read in the TLS. So I think that would be unfair to Russell. I think Russell, it wasn't the logic by itself, it was logic plus the new physics.
Right, okay.
And that continues to play a big role in Russell's thought. His thought on perception, for example. The term naive realisms, I've not been able to find the full Russell in the 50s. I assumed it was a 19th century term, but I've not been able to find uses of the term naive realism between one of Russell's books in the 50s. And there we appeal to the fact that modern physics has shown that colors, things are not colored, etc.
Right, yeah.
So Russell is, and I think for Wittgenstein in the Tractatus, in that one book,
right.
Of course, true. I want to turn you off. Comments. I have a voicemail. Listen to the voicemail. They're calling up. I think Wittgenstein was, of course, a bit of a Schwärmer for logic in the Tractatus, and of course, approaches himself for that later. But remember that Wittgenstein, before he started studying philosophy with Russell, worked on designing a jet engine for the jets. I mean, he was a trained engineer after all. In the Vienna phone book, Wittgenstein is listed as Ludwig Wittgenstein architect. Maybe that's true. So I think it was somehow but for Wittgenstein, but not for Russell. The physicists Wittgenstein respected, like Boltzmann, were anti-metaphysical. And that makes a big difference.
So might I suggest that we continue our conversation in the lounge over drinks? And thanks for